So starting chapter 6. Skip that first slide. So this is jumping back as a quick reminder. When the factor by grouping, are there commonalities between these two terms? Or these two terms? Or these two terms? You know, so some people could take like, well, this one has a 9 and that one has a 9, so I can rewrite it as 9abc squared plus 9bc plus, and then I've got the 6a squared bc plus 6ab. Now you didn't have to do that. Could have very easily have used them the way they were written, because the first two do have items in common to factor. But if I do it this way, then I'm looking at these two saying, all right, now what do both of these terms, right? And terms are things that we add or subtract. What do both of these terms have that can be factored out of them? Or what can be divided from both of them? They are both divisible by 9. They both have a b. And they both have a c. So what we're really doing when we're doing this is I'm saying, all right, well, if I divided this by 9bc, and I divided this one by 9bc, what am I left with?
C squared.
So I am left with, so the 9's reduce, sorry, that's an A. Undo that. The 9's reduce, the b's reduce, and one of the c's reduces. So in the numerator, I'm left with AC plus 1. Common mistake people are going to make is like, oh, that just goes away. It doesn't go away. Anything divided by itself is always 1. Plus, and then I look, these are both divisible by 6. They're both divisible by A. They're both divisible by B. So when I do that, so that'd be 6AB, 6AB. I am left with here, the 6's reduce, the A's reduce. Oh, no, they don't. There's 2 A's in the numerator, so one of the A's reduces. The B's reduce, so I'm left with AC plus 1. And then you look at that and say, well, this is the exact same as that. So up here I had 4 terms, 4 things that are being added. Down here I have 2 terms. Here's the adding. I have this whole thing. I have this whole thing. Since I have 2 terms that have something in common, which is the parenthesis set, I can actually factor AC plus 1 out of both of them. So if I do that, I divide this by AC plus 1. I divide this one by AC plus 1. AC plus 1 and AC plus 1, the whole thing reduces. The whole parenthesis set reduces, leaving me with 9BC plus 6AB. And then it's possible that some of you even recognized that this one, so now I have 2 terms. That's multiply. This term and this term. This cannot be factored. This has AC, that is a 1, but this can be factored. Both of these have something in common that can be, again, like reverse distributive propertied out. They are both divisible by B, what else? 3. So then I'm going to have that 3B out in front. There will be the AC plus 1. And then the B's reduce. This reduces to 3. The B's reduce. This reduces to 2. It would be 3C plus 2A. as a complete, fully factored when you do all the factor by grouping. Now, if you wanted, which wouldn't be a bad idea when you're just, did I get the right answer? If this is a test or quiz question, you have time, you'd go back and say, well, I could take this and do FOIL, then multiply by 3b, everything that I have, and if I do that, it should give me this full thing up here. When graphing, doing a absolute value function, whether you remember how it goes or what way to shade and all those other things, an absolute value function will be either a v that goes up or it's going to be a v that goes down. So then when you're graphing it, there's a couple ways to do it. But in this case, I'm going to look at this, and since out in front of the absolute value is a positive, right? There's not a negative out in front. That means that this absolute value is going to be an upward shaping V. All right? So one way to look at this is I take this and if I were to just drop the absolute value, y greater than x minus 3, and if I graph that first, all right, so then I'd say, well, minus 3 is my y-intercept. 1, 2, 3, 4, this is y. This is x. 1, 2, 3, 4. 1, 2, 3, 4. The y-intercept is negative 3. It's right down there. And my slope of the equation is the number in front of the x, which is 1. So my slope is 1, so that's 1 over 1. Rise over run, so I go up 1 over 1. Up 1 over 1. Up 1 over 1. And here's then the caution part. This is just greater than. If it's just greater than or just less than, my graph will be a dashed line. If it's greater than or equal to, less than or equal to, solid line. So I'm going to have a dashed line here that's going to go through those points. Try to make all right, about like that. Then I can take the same equation and do it as y less than. Actually, let's not even worry about the symbol there. If the absolute value of something is 3, then the number inside could be either 3 or negative 3. So to do that, I could also say, well, I'm going to graph negative x plus 3. So just changing the signs on both items. So if I do that, I go to the y-intercept, which is now positive 3, because that's the 3. Slope is negative 1, so that's down 1 over 1. Down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. Dashed line as well. That's not as straight as my other one was. And then I recall that the absolute value function is a v. And since it's a positive out in front of the absolute value, it's going to be an upward facing v. If there were like a negative in sign outside of the absolute value, it would be a downward facing v. So I look at my graph and say, well, my upward facing v is here, which means this down here is not part of the graph. And then I would go, all right, greater than, y is bigger than whatever this is. Bigger than means it would be shaded up above in that zone. Now, if you're not really quick about getting that, then there's always and this is always a reliable option, making a little t-table. Put in numbers. If I put in 0 for x, 0 minus 3 is negative 3. Absolute value of negative 3 is 3. Put in other numbers. I usually say, look for convenient numbers. What if I put in 3? 3 minus 3 is 0. Absolute value is 0 is 0. And then, again, pick another number, 4. 4 minus 3 is 1. Absolute value of 1 is 1. I could have put in other numbers, could have put in 2. 2 minus 3, negative 1. Absolute value of negative 1 is positive 1. And then I could go ahead and look at how that's going to graph. 0, 3, so that's 0 over 3 up. Zero over 3 up, that's that point right there, which, right there. 3 over 0 up. So 1, 2, 3, and then 0 up is that point right there. And yeah, it makes sense that all these are going to be in here. 4, comma 1, so 4, comma 1 is right there. 2, comma 1 is right there. And the minute you have two numbers that have the same y value, that means that the v, the center of the v is in between those 2 points, which it is, which was the 3, 0. So then it was here, dotted line going that way. Again, shading above. So either process works when graphing. So now, here's what I want you to do. Take a moment. I'll stop talking. And I want you to kind of work your way here, down, then here, down. So take a moment and see if you can simplify those. So when we're looking at that numerator, since there are two things and it's multiplying, that can reduce. Most common mistake I'm going to see people make, they're going to try to use this 2 and somehow reduce it in that 8, but you cannot do that. Because as we did up here on this problem, the only time you can reduce when we're adding is if both of them are divisible by 2. If both of these were divisible by 2, then I could, but I can't. So yeah, either you can add, multiply, that's 22 divided by 2 and get 11, or you can see right away, oh, those reduce, leaving me with 3 plus 8, which is 11. And now here, just anybody shout it out. No. 5x. 5x. Multiplying in the numerator, 10 times x. Multiplying means I can divide right away. 10 over 2 is 5.
I looked at the wrong one.
Okay. What's the next one? Just x. 2 divided by 2 is 1. Trick question. That one is simplified. There is nothing you can do. Most common mistake, I'll show you, and I'll put it in red because, right, when you see things in red with the little box through it, means don't do it. People will say, well, this is 1 plus x. Right? This would be a wrong answer. What people are doing is they're saying, well, if I reduce those, right? Or people will say, well, this is just x. Because, again, the argument they're making is, well, if those, they quote unquote go away, all right? In math, the only time things disappear, so to speak, is if they add or subtract to 0. 2 plus negative 2, 0. All right? That's the only time things can go away. Otherwise, in this case, they would reduce. So some people say, well, it reduces to 1, and then I'm left with x, so 1 plus x. Or they say this goes away and I'm left just with x. Also wrong. Both of these are not correct. The actual solution is the exact same answer that's written. It's 2 plus x, so that's 2 plus x over 2. There is nothing that can be done to simplify that anymore. Next problem. Answer is x. 2 divided by 2. It's this pretty much the same thing. It is exactly the same as this. It's just here we have the multiplication with the dot. Here we have multiplication with parentheses. And then lastly, here. Can this 2 reduce with that 2? Everybody shake your head and say no. No, it cannot. That 2 is trapped inside the parentheses. And the reason why this 2 cannot reduce with this 2 is because this x does not have a number in front of it divisible by 2. So for this one, to simplify, I would do distributive property, 6 plus 3x over 2, and that would be it. Now, you could, and it would not be wrong if you wanted to do this, you could say, well, it's 6 over 2 plus 3x over 2. That would be a correct statement. And then 6 over 2 is 3, and then that would be 3x over 2. You could do that as well. Depending on what math professors you might have in the future, some might prefer this as a single fraction. Others might prefer that. It's the same thing. All right. Generally speaking, this is the preferred route for many mathematicians. For lack of a reason other than that's just what we're so accustomed to, we would like to see it as just one fraction, not as like multiple terms. All right, so polynomials are to algebra what integers are to arithmetic. So back when you did and you wrote like add, subtract, multiply, divide, that's arithmetic. And then from that, we did all sorts of operations with those integers. Now we have algebra, which means we have equations, and we're going to do to all these polynomials in algebra what we did to the integers in arithmetic. We're going to add them, subtract them, multiply them, and divide them. When we do it, we need to consider some things. First thing we're going to consider is, can it be factored? That's why I have factor. So I look at this one and I say, can this be factored? Do these two terms have anything in common? No, they do not. Are they both divisible by 2? No, they are not. So at that point, this expression, it's called a rational expression. If you notice, there is no equal sign. So I cannot solve this. Common mistake when we're rationalizing and dealing with rational expressions is people say, oh, let's solve. Well, there's no equal sign in the original equation, so I can't solve it because that's not the point of the problem. You can only solve when there is an equal sign. Now we might say this and it will be equal to something, but that doesn't mean there's an equal sign in it, all right? So we're going to factor it first. That cannot be factored. Then we talk about the domain. The domain is all the x values. So the domain are possible x values. When talking about the domain, even though it's the possible x values, we usually say things like, is there anything that I cannot do? And you think about, all right, in fractions, what can we never have in fractions? Can never have 0 in the denominator. All right. Well, in this case, we have 2, which is fine. So no matter what I put in for x, this can never be 0 because there's no x down there. It's always going to be 2. All right. There will be other types of equations when we have a square root of something. You say, all right, well, what can we never do with square roots? We can never square root a negative number. So that might restrict my domain. In this particular problem, is there anything I can put in, or is there anything that I cannot put in for x in this fraction? All right, so if I do a positive number, even out to like an infinitely large positive number, will this fraction still reduce? Well, I mean, it may not reduce, but I mean, I can take whatever number this is on the top and divide it by 2, and I'll get a number. If I take a 0, put 0 in here. 0 plus 7 is 7 over 2. 7 over 2 is 3.5, so that's fine. That's a number. That's not a problem. If I put in an exceptionally large negative number, negative 1 million times 3 is negative 3 million plus 7, negative 3 million plus 7, right? I can divide that by 2. I'll still get a number. So in this particular situation, my domain can be any x value. When it's any x value, we say my domain is all real numbers. That word is real, R-E-A-L, even though my my handwriting is atrocious this morning. So all real numbers. There is a shorthand symbol that we use in mathematics that stands for all real numbers, and that's that number right there. It's like a capital R with an extra leg on it. All right. When dealing with rational expressions, after I factored it, I've determined what my domain is, possible values, then I'm going to simplify it. Well, again, this one here, we couldn't factor it, so it is simplified, so that problem in terms of a rational expression is done. Can't factor it, can't simplify it, but we're going to talk about the domain, all possible x values. Now we work to another one and say, all right, can this be factored? Well, in the denominator, I have 2x squared plus 7x plus 6. We're trying to think, is that something that can be factored? 2, 7, and 6, well, even number, odd number, even number, so they're not all divisible by 2. But it is a squared function, so I'm thinking, can it be factored into something like this? All right. If this is 2x and this is x, and this gets to the fact that I've been doing this for a long time, are there numbers that are going to multiply to 6 here and here, so like 2 and 3, that when multiplied by the first and the last will give me 7x? They're both going to be positive. How do I know they're both positive? Multiplies to a positive, adds to a positive. They're both positive. If it multiplies to a positive and adds to a negative, they're both negative. And if I were to do 2 here and, no, that's not going to work. Let's see. And it's possible that it's not factored. So I'm thinking of numbers like 2 and 3. If this was 2 and that was 3, then when I multiply insides, it would be 2x. Outsides, it would be 6x. And 6x plus 2x is 8x, not 7. If I switch them around and put a 3 here and a 2 there, that would be 4 plus 3. Well, that is 7. So this is, come on, 2. This one's 3. And what I was saying is, so first, 2x times x is 2x squared. Outside, 2x times 2, that's 4x. Inside, 3 times x, that's 3x. So 3x plus 4x is 7x. And then 3 times 2 is 6. So my denominator could factor like this. 7x minus 2 in the numerator. I now have it factored. Then I look and say, all right, do we have any restrictions on the domain? In this case, I have a fraction, and I know that in a fraction, if I ever have 0 in the denominator, no matter what the numerator is, k for some constant, that this is an undefined expression. You can never have 0 in the denominator. So I say, well, all right, when does 2x plus 3 equal 0? When x is negative 3 halves. If you see what I did there, took this thing, set it equal to 0. Why did I do that? Well, if I have 2 items in the denominator that are multiplying, they are multiplying to 0. If they multiply to 0, then I'll get 0 in the denominator. So if x is negative 3 halves, I put that in there. 2 times negative 3 halves is negative 3. Negative 3 plus 3 is 0. I'd have 0 times something, 0, and I cannot have 0 in the denominator. So I'm actually solving one portion of the denominator that will tell me what I cannot use for x. Then I look at x plus 2. What makes x plus 2 equal to 0? x is negative 2. So for my domain, x cannot be negative 3/2. X cannot be negative 2. And the way we would then write that is using what is called set notation. So set notation is a method for identifying what values I can have. So x, put a little colon there. So x can be anything from negative infinity up to negative 3/2. Or, I missed, I'm gonna have to go back and erase something there, sorry. The lower number is negative 2. Or, negative 2 to negative 3/2. Or, negative 3/2 to positive infinity. Set notation, parentheses are very important. What they mean is I can go up to negative 2 all the way up to, but not actually including negative 2. So when we're drawing a number line, it would basically be like, all right, I have right here negative 2, and here I have negative 3/2. I'm going to have an open dot and an open dot, and I have everything in between there, everything above it, everything below it. And the reason why I have parentheses on the negative infinity is you can actually never get to negative infinity. That's why it's open parentheses. If it included 2, it would be a bracket. So if it were a bracket, it's not a very good looking bracket there. If I had a bracket with negative 2, that would imply a closed dot. But in this case, since I cannot have negative 2, that's an issue with my denominator. I cannot have it, so it's an open it's a parentheses, not a bracket. And if this is all new to you, I would not be surprised. If some of you have seen it, it just seems like it's a lower and lower proportion of teachers who teach set notation. All right, so that's my domain. On a real simple level, I would write anything but negative 3/2 and negative 2. Slightly more sophisticated for mathematical language, I could say all real numbers except negative 3/2 and negative 2. Even more sophisticated math language would be this. What would I expect you to do? Either all real numbers without those two. So you'd say all real number, x can be any real number except negative 3/2 and negative 2. I also love this, but just this is not going to be enough. If you say, well, x can't be negative 2, x can't be negative 3/2, you haven't told me what it can be. Any real number but those two, now you've told me what x can be, and that's what the domain is. There you go. So for those that weren't in class, we just spent some time on Desmos graphing this to see why negative 2, negative 3/2 are significant values, and then what happens as it's called as we approach the end of a function towards negative infinity, towards positive infinity. But we'll be doing more of that in class as we learn, as we apply these aspects to bigger problems later. We're going to do the same thing here. Start by factoring. In that numerator, is there a greatest common factor? No, there's not. This is 6, that's 1, that cannot be factored. Is this a special form of a quadratic? It is not. It is not the difference of squares, and that's the one we have. So the numerator cannot be factored. Can my denominator be factored? No, it cannot. X and 3 have nothing in common. A very common mistake people will make is they'll say, well, 6 divided by 3. Can't do that because the plus, right? Like we did when we were warming up and doing some earlier problems. I can only reduce when there's adding if everything has the same common factor. If all 4 of these were divisible by 3, then yes, I could reduce it. But I cannot factor it. So then I look and say, what about the domain? Domain, when we're dealing with fractions, is when is the denominator, not x equals 0, x plus 3 equal to 0. When x is negative 3, the denominator is 0. So my domain is all real numbers except x equals negative 3. In set notation, that would be negative infinity up to negative 3, or from negative 3 to positive infinity. That's my domain. And then lastly, can I simplify it? Which I didn't do on the last slide. We couldn't do it on the last problem either. There's nothing in here that can reduce. On the last slide when we had 7x minus 1, or 7x, whatever it was, minus 2 in the numerator, that parenthesis set was not identical to a parenthesis set in the bottom, so they could not reduce. All right. Take a moment and see if you can factor. So this one can be factored. So take a moment, see what you can factor, see if you can identify what the domain is then, and then we'll come back together to simplify. So if you're working with the factoring, the numerator is only one term, so it just stays 2x squared. But then I look at the bottom saying, oh, wait, 10 and 2 are both divisible by 2. That's why I wrote the 2. They both have an x. Actually, this one has 3 of them, so I can take 2 out. This has 2 of them, I can take 2 out. So I'm reverse distributive propertying, if that's a word or not. So taking that 2x squared, putting it out in front. Now remember, when you're factoring, that once you figure out what you're factoring out, make sure you put it out in front of the parenthesis set. So 2x squared, and then I'm here, 10 over 2 is 5, x cubed over x squared is x, 2 over 2 is 1, x squared over x squared is 1, so that's 1 and it's minus 1. So now I have it factored, and then I talk about domain. What can I not have? So now I've got some squareds. Are there any numbers that I cannot take the square of? No. Like anything. I take a negative number times a negative number? Sure, I can square that. Any number I want, I can square it. So I'm good there. Is there anything I can't have? I cannot have 0 in the denominator again. So I'll look at this, say, all right, I have two things being multiplied. I have 2x squared and I have 5x minus 1. So I'm going to think, well, what makes 2x squared equal to 0? I'll divide both sides by 2, x squared equals 0. What number times itself is 0? 0. All right. Then I take 5x minus 1, set it equal to 0. 5x equals 1, x equals 1/5. So for my domain, I have all real numbers except x equals 1/5 and x equals 0. All right. I guess another way, if you wanted to do this, we could say, let's see. Yeah, it's not, we'll just go back to set notation. Negative infinity up to 0, or 0 to 1/5, or 1/5 to positive infinity. And then when I'm done with that, I look back up to this equation and say, can this be simplified? Is there anything that's identical numerator and denominator? I can see a couple of head bobbles of yes, that's correct. In the numerator, I have 2x squared. In the denominator, even though it's not written in parentheses, it could be there because it's multiplying. I have 2x squared. Those 2x squared divided by 2x squared is 1, leaving me with h of x equaling 1 over 5x minus 1. And this is very important for, again, for later on. If I were to reduce first, I'm actually going to lose out on the fact that my equation cannot be 0. So then I'd only have 1 over here. So I'm like, oh, my domain is anything but 1/5. Since this reduces, again, it doesn't disappear, but it reduces. But in the original equation, it would still be considered a point of discontinuity. That means on the graph, if I'd be on the graph and going, when I got to 0, even though the graph would look like it's there, there'd be an open dot on my equation when I would be graphing it. I'll do this one a little bit quicker for us. So in the numerator, I have, both are divisible by 2. I'm left with 9 minus x squared. In the denominator, the two numbers that multiply to -3 and add to -2 will be -3 and +1. And then I realize, actually, I can factor more because that numerator is now one of those special forms. It's a difference of squares. 9 is something squared, and x is something squared. So my g of x can be factored even more, so it's going to be 2 times 3 plus x, 3 minus x. In the denominator I have x plus 1 and x minus 3. For my domain, I don't have square roots. All I'm worried about here, again, fraction, cannot have 0 in the denominator. X cannot be -1. X cannot be 3. If x were 3, I'd have 3 minus 3. That's 0. 0 times something is 0. 0 in the denominator, undefined. X cannot be -1. If I did, -1 plus 1 is 0. 0 times anything is 0. So my domain is all real numbers except x is -1 and x is 3. Simplify. Is there anything in the numerator that's also exactly in the denominator? Yes. Ooh, careful. Almost. These two are almost identical. How are they different? One has a positive 3, the other one has a negative 3. One has a positive x, the other has a negative x. It can simplify, and this is just a little bit of extra thinking now as we go along with these. I am going to, from this parenthesis set, factor out a negative 1. So I'm going to take 3 divided by negative 1 and negative x divided by negative 1. When I do that, that negative 1 will be out in front. So negative 1 times, and then I'll have the 2 that's out there, the 3 plus x that's out there, and then 3 divided by negative 1 is negative 3. Negative x divided by negative 1 is positive x. I then have x minus 3. Denominator still is x plus 1. X minus 3, and now I can reduce the x minus 3 and the x minus 3. So my g of x function would be negative 1 times 2, negative 2, 3 plus x, which we could leave like that. Most mathematicians like to write it the other way around with the x first, but if you have it as 3 plus x, that's fine. Denominator will be x plus 1. At which point then I am done simplifying. Got to be careful. This x cannot reduce with that x. They're both trapped with pluses. And the only way when there's adding that I can reduce is if everything that's being added has the same thing. So if all 4 of these had x's, then yes, I could reduce. But I cannot in this case. So even though, what I was saying, my domain still is I cannot have x equaling 3. But if I would find g of 3, if I plug in 3, negative 2 times 3 plus 3 over 3 plus 1, right, just replacing that x. In the numerator, I'll have 6 times 2, which is negative 12. In the bottom, I'll have 4, and that's negative 3. So technically, when I put 3 in to this equation, I get an answer. If I put 3 into this equation, I will have 0 in the bottom and I'll have undefined. This was the original equation. My domain means that my restrictions are I cannot have 3 as an x. It's all real numbers except those 2. But after I simplify it, that this point is called point of discontinuity, reduces, it disappears. So repeat your question then.
Is that the final answer?
This would be the final answer after simplifying, yes. Yep. Lots of simplifying going on here. Dividing by fractions is the same as multiplying by reciprocal. So I'm going to go ahead and start working through this problem, also by factoring. I notice that this is a difference of squares. So it will factor x plus 5, x minus 5. In the denominator, I have x plus 5 squared. I'm going to write that out longhand as x plus 5 times x plus 5. Don't make the mistake of people saying, oh, it's going to be x squared plus 25. That would be 100% wrong. Exponents outside of parentheses can only go into each individual item if we are multiplying. Just like in reducing, can only do it when we're multiplying. We can't do it when we're adding. So it says, squared means times itself. Times, let's see, 3x plus 5, both are divisible by 3. So that will then leave me with x plus 5. In the denominator, and I'm just going to go ahead and make one giant fraction, I have 4x. And I'll have that as a parenthesis just to help keep track of it. I'll put that 3 in parentheses too just to keep track of it. divided by a fraction means multiplied by the reciprocal. X is in the numerator. Denominator, I'm going to take this expression now and factor it. Two numbers that multiply to x squared are x and x. Two things that multiply to negative 10 that add to negative 3. Are there two things that multiply to negative 10 that add to negative 3? Negative 5, positive 2. They multiply to negative 10 and they add to negative 3. My domain. When I look at this, all real numbers except what makes this 0?
Positive 5.
Negative 5?
Yeah, sorry.
Except negative 5. What makes this 0? Negative 5. What makes this 0? 0. 4 times 0? What makes this 0? Positive 5. What makes this 0? Negative 2. So it's all real numbers except those 4 values. And then my last step is to simplify if I can. Looking up here, I have multiply between parentheses, multiply between parentheses, multiply, multiply. Each set of parentheses are multiplied. In the denominator, all sets of parentheses are multiplying as well. So I look to see what is identical numerator to denominator. X plus 5 and x plus 5. I have an x minus 5 and an x minus 5 over here. I have an x plus 5 and an x plus 5 there. I have just an x and just an x. So in the numerator, I have 3, and that's it. In the denominator, I have a 4 and a parenthesis and an x plus 2. This would be the fully simplified version of this big rational expression, knowing that my domain can be any number except I cannot use negative 5, 0, 5, or negative 2 for x. Set notation for this would be complicated. Be, negative infinity up to negative 5 to negative 2, negative 2 to 0, 0 to 5, and then 5 to positive infinity. It'd be a messy right up. This would be a faster way and quicker way. Easier, simpler, cleaner. All right, take a moment and simplify each of those for me, please. When adding fractions, what do we need to have? Common denominators. So what was that first one? 4/8, which then you can reduce to 1 over 2 if you want. I will, believe it or not, be okay with this. If you don't reduce it to this, that's fine with me. If you just leave it as 4/8. We'll always reduce and simplify our rational expressions, but just actual numbers for fractions don't bother me as much. Second one.
1 to x over 8.
I'll agree with it over 8,
X plus 1.
x plus 1. X plus 1 over 8. We're adding, so they're just going to add. Common mistake is people will multiply accidentally. Well, now you had to change it to common denominators. So 3/4 was the same as something over 8, which is 6 over 8. 7/8.
Could you not use the bolts?
All right, so then I have this one also needs to be over 8. How did I make that 4 into an 8? I multiplied both the top and the bottom by 2. So if you wish, down here, I'll show it. So x over 4, I'm going to multiply it by 1. You hear me say this a lot. Multiplying by 1 does not change the value, just changes how it looks. 2 over 2 is 1. Anything times 1 is itself. So this will be 2x over 8, which is the exact same thing, but now at least I have common denominators. Two x plus 1 over 8. Next one, I have 8 and I have x. What is my lowest common denominator going to be? 8x. So in order to have the second half of my equation as 8x, I need to multiply it by 1. It's kind of a messy one. X over x is 1. So it then becomes x over 8x. This first one I'm going to multiply by 1 as 8 over 8. So intermediate step, 24 over 8x plus x over 8x will be 24 plus x over 8x. And I cannot simplify that. How do I know? 8, 24, and x do not have common factors. 24 and 8 do. X and x do, but all three of them do not. My common denominator here will also be 8x. So this is x over x. So it'll be 3 over 8x plus x over 8x will be 3 plus x over 8x. Is this a common denominator? Yeah. So every once in a while you'll get those and you're like, oh, that's so much easier. But we sometimes look at it having done all of these and go, oh, I need to convert it to something. Be careful, sometimes they are still the same ones, kind of intermixed. 2 plus x over 7 minus x. And again, those x's cannot reduce. Adding and subtracting can't reduce unless all four of them have the same thing. We'll come back to the next one after we finish this last one. The last one, they do have common denominators. X minus 5. I'm going to write it like that. It's going to be all over 2x because I can combine. And I'm doing it like that because it's minus this time. So you got to be cautious with the minus. The minus means minus the whole thing. So minus an x. And subtracting a positive 5. Minus 5. So that negative has to go to both terms. Like, basically distributive property. So then, inside, to simplify, I have x minus x, that's 0. Negative 5 minus 5, negative 10 over 2x. And now I can reduce, because I only have terms. Negative 5 over x, both are divisible by 2. Going to give us some space on this one. Like we had up here, I had 8x and I have 8. Or I should say, it's more like this one over here. I had x and I had 8. My common denominator is going to be 8 times x. So this had to be multiplied by 8 over 8. This had to be multiplied by x over x. On this one, my common denominator will be 7 minus x times 7 plus x. So then I have to think, all right, how do I get this to have this as my denominator? Well, I need to take the 2 over 7 minus x and multiply it by 1. And the one that I'm going to choose is 7 plus x. And then I'll have plus. And the second half of my equation is x over 7 plus x. But I want it to be 7 plus x times 7 minus x. So I'm going to multiply this by 1. Specifically, 7 minus x and 7 minus x. Here in the numerator, I'm going to have 7 plus x times 2. I'm going to write it the other way for no other reason than we typically like to put the numbers first and parentheses later. In the denominator, I'll have 7 plus x times 7 minus x. Over here, I'll have x times 7 minus x. In the denominator, I'll have 7 plus x times 7 minus x. I rewrote these in the other order. Instead of 7 minus x times 7 plus x, I wrote it 7 plus x times 7 minus x. That way then, at least they look the same. They are the same, but now at least I feel better because they look the same. Now, numerator, going to simplify that. 2 times 7 plus x. 14 plus 2x, distributive property. Since they have the same denominator, I'm going to go ahead and combine those two fractions into one fraction. So now it'll be plus. And then distributive property, 7x minus x squared. Combine like terms, negative x squared plus 9x plus 14. All over x plus 7 and 7 minus x. And then you might think, are we done? It looks like we should be done. But now I've simplified the numerator when I combine them and I have a trinomial. So usually when I see that, I think, well, can I factor that? If I factor a -1 out to start with, I'll be left with x squared minus 9x minus 14. And you might say, well, why are we factoring that -1 out? I really like my trinomials to start with a positive x squared. Down here I have x plus 7. And some of you noticed, here it was 7 plus x. Here I wrote as x plus 7. Adding can be done in either direction. Subtraction can't, so this one stays as 7 minus x. So now I'm thinking, are there two numbers that multiply to -14 that add to -9? What numbers multiply to -14? 14 and 1, but it's got to be -14, so -14 and +1. They add to -13. 7 and 2, they multiply, but it would have, one of them would have to be negative. So if it's -7 and +2, that's -5. 7 and -2 would be +5, not -9. So not quite. Since it cannot factor like this, this now would be considered done. Or you could have left it like this. But I point that out because sometimes, especially now that we're going to be adding and subtracting these rational expressions, when you get them finally added or subtracted, you might go, oh, now I have something that might be able to be factored. So we're always in this process of simplify, factor, or in other cases, factor first, then simplify. When we get to these, it can be challenging to look and say, oh, well, I have these two different denominators, so I'm going to multiply them first, which is always a possibility, but I also look and see that this can be factored and that can be factored. So this could be factored into 3 times a plus 3. And this could be factored into 5 times a minus 3. So now, when I think about what my common denominator is going to be, my common denominator will be 3 times 5 times a plus 3 times a minus 3. It's all of those things. This, and this. How do I get this one to have this as my common denominator? Multiply it by 1. Specifically, I need there to be, in addition to the 5, there needs to be a 3. So my denominator here will have a 3. In addition to the a minus 3, there needs to be an a plus 3. So this will be 3 times a plus 3. 3 times a plus 3. To the left side of that fraction, going to multiply that by 1. It also needs a 5 in the denominator and an a minus 3 in the denominator, which means there will be a 5, a minus 3. So very sophisticated. Again, this is 1, so I'm multiplying this fraction by 1, this fraction by 1, so that I can at least have a common denominator. So now this numerator times 2 will be 10 times a minus 3 plus this numerator times that will be 15 times a plus 3. So I did the liberty of multiplying the numbers first. (10a minus 30) plus 15a plus 45 all over, went ahead and did the multiplying there, 3 times 5, 15 times a plus 3, a minus 3. In the numerator, I have 10a and 15a, which is 25a. I have negative 30 and 45 added, so that's plus 15 divided by 15, a plus 3, a minus 3. And as always, you should always be checking to make sure I'm doing my math the right way. I'm adding where I'm supposed to be adding. When I've subtracted the right amount, 45 minus 30. Or up here, I didn't lose track of negatives, which I don't believe I did. Almost done. That numerator can be factored once I've combined it. They're both divisible by 5. 5a plus 3. 15a plus 3. A minus 3. And then 15 and 5 are reducible, 1 and 3. For a final answer of 5a plus 3 over 3, a plus 3, a minus 3. And if you had to talk about domain, I cannot have positive a, so a cannot be positive 3, a cannot be negative 3. That would give me 0 in the denominator. Same idea, but this one would be subtracting. The key item is then making sure that this negative gets distributed in. This is 3a plus 3. This is 5a minus 3. Same idea, right? This gets multiplied by 5a minus 3. 5a minus 3. This is multiplied by 3a plus 3. 3a plus 3. This denominator times this whole fraction, top and bottom. This denominator times this whole fraction, top and bottom. 10 a minus 3 minus 15 a plus 3. Remembering to distribute that negative when I simplify. 10a minus 30 minus 15a minus 45. All over 15a plus 3, a minus 3. Negative 5a minus 75. All over 15, a plus 3, a minus 3. Again, that numerator can be divided by 5. It'll factor out. It'll reduce to give you your final answer. Biggest reason why I did that one, just to remind you that when there's that negative, when you're subtracting fractions, make sure that negative goes to the whole fraction. Just essentially making sure you're using distributive property to get that moved out. Those are the items that are listed on our canvas for the Check Your Understanding problems. As always, my constant reminder, these are odd problems so that you can be looking to check your answers. And if you don't get the right answer, that's when you say, I need to go back and look at my notes, maybe reread or watch one of the videos. Email Mr. Steffen and set up a time to go through problems before class, after class, or on some other day, letting me know in advance in case I'm not going to be here, which is my next point. I will not be here on Thursday. There were 2 days I knew I was going to be missing this term. They just were really close to each other. So Thursday I will not be present. I'll have a video up later today with all of the chapter 6.3 and 6.4 notes. For you to watch on the video, there will be instructions about what your assignment is to prove that you watched the video. Make sure you watch the video and then do the assignment by the date that it's due, which is in Canvas, by the way, with a due date on there. I think I put it on there for Friday, but if you get it done sooner than that, that's fantastic too. That's all I got for today.